Hello and welcome back to the Operations Research 1 course. Today we are going to talk about something that is totally new because we have not talked about this at all. It is called the dual linear programming. So let's start. So for a linear programming model, there is another linear programming that is called the dual. So if we formulate a problem into a linear programming model, that linear programming problem is called a primal. Well, it's just a name, okay? It's just to differentiate between that. This model is the primal, and there is another model that we'll call the dual linear programming. Why we would like to study this dual linear programming? Well, because the dual linear programming provides some economic insights into the problem. We can also have some additional insights about the sensitivity analysis that we've learned before, and also advanced topics in linear and nonlinear programming. Quite a lot of them use the duality concept. That's why it is important to learn about the dual linear programming. Before talking about how to find the dual linear programming, let's start by discussing what is a normal maximization problem. Later, I will also talk about normal minimization problem, but let's start with maximization. So when we talk about duality and using this textbook, the convention is that for maximization problem, we will always use the notation Z to denote the objective function and then X to denote the decision variables. Okay, now a maximization problem is called normal if all constraints have the sign of less than or equal to, and then all variables have the sign restriction of greater than or equal to. So to summarize, if you have a maximization problem and then all constraints is less than or equal to, and all variables have the sign restrictions of greater than or equals to 0, then we call this maximization problem as a normal maximization. Now for minimization, the convention is that we are going to use W to denote the objective function and Y to denote the decision variables. I think there is a typo here in your textbook. This should be Y as well. Okay. Anyway, for a problem to be called normal minimization, all constraints must have the sign of greater than or equal to, and then all variables must have the sign restrictions of greater than or equal to. So all constraints must be greater than or equal to, and all variables, notice here that variables must have the sign restrictions of greater than or equal to 0. If these two requirements are satisfied, then we call this minimization problem as a normal minimization. Now it's time to find the dual of a normal maximization problem. So in general, we can say that normal maximization problem looks like this, right? With those two requirements, the constraints and the sign restriction of all variables. Now we are going to put this into a table which will help us to read the dual linear programming of this normal maximization. Okay, from this table I'm going to cover the minimization part because that part is related to the dual, so I will cover this. I will cover also all the signs here in front of the C's, so I will cover that for now, and let's just see how this table is related to our normal maximization problem. Okay, so in this table you will read this table for maximization. You will always read this table across the rows. So here, for example, you have n variables, so you write down x1, x2 up to xn as the title of the column. Then for each row here, you simply write down the coefficients. So a11, a12, a2, a1n for the first row, less than or equals to b1. So this is the first constraint. And here's the second constraint, and then here's the final or the m constraint. Okay, so you read that across the rows. Now you may also put the sign restrictions here above the title of the column. So x1 greater than or equals to 0, x2 greater than or equals to 0 up to xn. Now finally, you put the C here, the cost of each decision variable, at the bottom. Okay, so it's a bit the opposite of how we write down the formulation usually. So the sign restriction goes on the top, and then the cost of each variable in the objective function goes to the bottom of the table. So this is how we represent our normal maximization into this table. Okay, make sure you may ensure yourself that this table, the way we write down like this, is indeed representing the normal maximization problem that we have. Now that we have written down our normal maximization problem into the table, or we can also call this given linear programming as the primal linear programming, now let's use this table to find the dual linear programming. Okay, so the very first thing is that because the primal linear programming is a maximization, the dual is a minimization. Okay, so you write down minimization and you will minimize W. Okay, because the convention is for minimization, we will use W to denote the objective function. Okay, so you write down minimize W. And then the second thing here is that for each constraint that you have on the primal problem, so you have 1, 2, up to m constraints, means that you will have m variables in the dual. Okay, so for each constraint in the primal, you write down the dual variable. Again, remember, because the dual is a minimization, here your variables are y1, y2, up to ym. So again, let me repeat, if you have m constraints in the primal linear programming, in the dual problem, you will have m variables. Okay, so you have m constraints in the primal, you will have m variables in the dual. So we have defined that our dual problem will be a minimization problem, minimize W, and then we have also defined that we are going to have m dual variables from y1, y2, up to ym. Now let's define the sign restrictions for the dual variables. First, I would like you to notice that each dual variable comes from a constraint in the primal problem, right? The first dual variable y1 comes from the first constraint in the primal. The second dual variable comes from the second constraint in the primal problem. So it means that we need to check whether the primal constraint is a normal constraint or not. So recall, in the maximization case, a constraint is called normal if the sign is less than or equal to. So the first constraint in the primal here, it is a normal constraint for maximization. As the result, the dual variable corresponding to this constraint has the sign restriction of a normal variable in the minimization, because the dual is minimization. Remember that the normal variable in the minimization has the sign restriction of greater than or equals to 0. So that's why the sign restriction for y1 is greater than or equal to 0. Let's do the same thing for y2 once again. Y2 comes from the second primal constraint. So this is your second primal constraint. Your primal problem is a maximization. So the constraint with the sign less than or equal to is a normal constraint. It is a normal constraint. As the result, the dual variable corresponding to this constraint is also a normal variable. And then because your dual is minimization, the normal variable in the minimization problem has the sign restriction of greater than or equal to 0. So that's why y2 is also greater than or equal to 0. Okay. Now because this is a normal max problem, so all constraints are normal, that's why all dual variables are also normal. They all have the sign restrictions of greater than or equals to 0. Okay, so the reasoning is again because they come from normal constraints. They are all constraints are normal in a maximization for primal. That's why the sign restriction for the dual variables are also normal, which is greater than or equals to 0. If the primal constraints results in dual variable, now the primal variable results in dual constraint. Okay, so now in the previous slide we talked about the row. Now we are going to talk about the column. So each of this column will be a constraint in our dual problem. Okay, now let's talk about these signs. Greater than or equal to, greater than or equal to. Now think about the variable. The primal variable x1, x2, and xn, they are all greater than or equals to 0, the sign restriction of those variables. Which means that in the primal problem, maximization problem, they are all normal variables. Normal variables will result in normal constraint in the dual. So normal variables in the primal will result in normal variables in the dual. Now, our dual problem is a minimization. Remember again, for minimization, the sign of the constraints of the normal constraints are greater than or equals to. So that's why we put the sign greater than or equals to here. Okay. So let me repeat the reasoning here. Because they come from, they here means the dual constraints. The dual constraints comes from normal variables in the primal problem. They also normal constraints in the dual problem. Our dual problem is minimization, so our dual constraint have the normal sign which is greater than or equal to in the normal minimization. Now what we can do to obtain the dual is to read the table down, which look like this. So we are going to read this table according to the column. Okay, let me change the slide to make this clearer. Okay, so we have completed all the information that we need to read the dual problem of the given primal maximization. So let's start by writing down that our dual problem is a minimization problem, minimize W, because our primal is maximization. Okay. Now let's talk about the constraint. Here what I mean by reading the table down means that for the first constraint, you look at the first column. You look at the first column and this is how you read it. A11 times Y1. plus a21 times y2 plus up to am1 times ym greater than or equals to c1. So that's how you read the first constraint. For the second constraint, it's very similar. You just look at the second column. Okay, and then a12 times y1. Don't forget to multiply it with the corresponding dual variable. a22 times y2 up to am2 times ym greater than or equals to c2. So that's the second constraint. You do the same thing up to the nth constraint, a1n times y1 plus a2n times y2 plus amn times ym greater than or equal to cn. Okay, so that's how you read the constraints. For the sign restrictions is quite straightforward. You just look at this column and you just write down all the sign restrictions. Okay. Now for the objective function, it's a bit, I would say not very intuitive, at least for me, but this is how you do it. So for the objective function, you are going to look at the right-hand side of the primal problem. So b1 times y1, and then you just ignore the sign of the constraints in the primal problem. So do not look at these signs. So you just read this b1 times y1, b2 times y2, up to bm times ym. Okay, so this should be ym. There's a typo on your textbook. Okay, so that's how we are using this table to read the dual problem of the given primal problem. If you notice that the dual is a normal minimization problem, you are correct. So the dual of a normal maximization problem is a normal minimization problem. And the other way around is also correct. The dual of a normal minimization problem is a normal maximization problem. Or in other words, if you find the dual of this problem, you will get this maximization problem again. Okay, so if you keep finding the dual, you will just alternating between the max and the min, and both are normal. So let's apply what we've seen before using this example, a normal maximization problem. So you put this primal problem into the table. So for example, this is 861 less than 48. That's the first constraint. And then you put the sign restrictions here on the top. And then the title of each column is the primal variable. And then at the bottom of this of each column, you put down the coefficients in the objective function, 60, 30, and 20. Remember that we have not talked about these signs, okay, because those correspond to the dual problem. Okay, so up to here you have input all the parameters in the primal maximization problem. Now let's fill this table with the dual information that we need. So first thing is you write down this is our dual is a minimization because the primal is a maximization. So you write down minimize W. Then for each of the primal constraints, we have a dual variable. So in the primal, we have 3 constraints. It means in the dual, we have 3 dual variables, y1, y2, and y3. Because all constraints in the primal problem, they are all normal constraints. So you see that all constraints have the sign of less than or equal to. They are normal in a maximization. So our dual variable, they all have the sign restriction of normal variable in the minimization. So in the minimization case, the variable are normal if they have the sign restriction of greater than or equals to 0. Now for the dual constraints, for the dual constraints, the sign is determined by the sign restriction of the primal variable. Our primal variables, they are all normal variables. The sign restriction x1, x2, x3, they are all greater than or equals to 0. So our dual constraints, they also have normal signs for these constraints. For the minimization case, the normal sign for the constraints is greater than or equals to. So we write down here greater than or equals to. Okay, because they come from normal variables. See the columns x1, x2, x3. They are all normal variables for the maximization case. So our dual constraint are also our dual constraint are also normal constraints in the minimization case. So read the table down to obtain the dual. So the first column says 8y1 plus 4y2 plus 2y3 greater than or equals to 60. So do the same thing up to the third constraints, and then the sign restrictions y1, y2, y3 greater than or equals to 0. And then for the objective function, minimize w equals, again, when we are reading the dual, you just ignore the original sign of the primal constraint and you just read it down. 48 times y1 plus 20 times y2 plus 8 times y3. So that is our dual LP. So do we always have to use the table to find the dual? Well, the answer is no, not really. For me personally, I would prefer using this transpose idea to think about the relation between primal and dual. It might be useful for you as well, so I will just discuss this quickly. So in my mind, I will, so on the left here is the primal LP. So in my mind, what I'm doing is I think that, okay, I will transpose the objective function of the primal to become the right-hand side of the dual. And then the right-hand side of the primal to become the objective function of the dual. So that's what I do first. And then I will transpose the content of the constraints. So the first row in the primal becomes the first column in the dual. The second row becomes the second column. The third row becomes the third column. Okay, so you have finished with all the numbers. Now to determine the signs, the sign restrictions, and the sign of the dual constraints, you only need to think about, okay, so this constraint comes from the first variable. Is the first variable normal? If the first variable is normal, then the constraint is normal. Same thing with variable. Let's say you'd like to determine the third variable. Third variable comes from the third constraint. Is this third constraint in the primal problem normal or not? If it is normal, then the sign restriction of your dual variable, of your third variable in the dual, is also normal. Now, you really need to be careful about what is normal in a maximization problem and what is normal in a minimization problem. It really helps to really remember what is normal in which case. Okay, so that's the end of this video. In the next one, I'm going to talk about how we may find the dual of a minimization problem. See you on the next one. Thank you.